Hello everyone. My name is Harun. I am an assistant professor in the Department of Astronautical Engineering at Erciyes University. Welcome to the 6th International Conference on Materials, Chemistry and Environmental Engineering. In my presentation, I will discuss assessment methods for the flying quality of fixed-wing unmanned air vehicle. The scope of this presentation is on flying qualities, closely related to and sometimes confused with handling qualities, controllability, and maneuverability. The concept of handling qualities encompasses the pilot's role, considering their capacity to accurately discern the aircraft's condition through oral and visual cockpit alerts. This concept further entails the execution of the requisite flight mission with an acceptable workload. Controllability is defined as the extent to which compensation is necessary to sustain a specified flight condition, along with the availability of control merges. As illustrated in this figure, the system integrates pilot control inputs with the aircraft's subsequent response, combining the aircraft's inherent properties with the mechanical characteristics of control inputs. Maneuverability is defined as an aircraft's capacity to transition from one trim condition to another. Stability is defined as the tendency of an aircraft to return to its trim condition subsequent to an external disturbance. Stability and maneuverability are intrinsic aircraft properties that contribute to the definition of flying qualities. In order to assess flying quality, we must first analyze flight motion. From a system dynamics perspective, under the assumption of linear and time-invariant flight dynamics, we can conclude that 6 degrees of freedom flight can be regarded as a superposition of longitudinal and lateral motions. Longitudinal motion is typically divided into short period and phygoid modes. The short period mode is important for flying qualities because pilots directly experience it when handling the aircraft. Lateral motion can also be assumed to comprise Dutch roll, spiral, and roll subsidence modes. All 5 modes should be evaluated in terms of the aircraft's flying qualities. Recently, many methods have been developed to evaluate these modes. Although our focus is on flying qualities, more research has been conducted on handling qualities. One of the most common methods for assessing an aircraft's handling qualities is the Cooper-Harper Handling Qualities Rating Scale, which is shown in the first figure, the left one. It was created to standardize the process by which pilots provide their subjective opinions on an aircraft's handling characteristics. It attempts to evaluate an aircraft handling qualities based solely on qualitative data. By sequentially going through the Cooper-Harper scale, engineers hope to receive specific diagnostic feedback on how the aircraft performed a particular task. In fact, the pilot's comments on how the aircraft flies are often far more valuable than any objective criteria. The scale requires the pilot to answer specific questions with a definitive yes or no. This deals to a pilot rating ranging from 1 to 10. A rating of 1, 2, or 3 equals to level 1 handling quality. Similarly, 4, 5, or 6 equates to level 2 handling quality, and a rating of 7, 8, or 9 equates to level 3 handling quality. The second figure shows the most widely accepted handling qualities rating scale for unmanned aircraft systems. It modifies the Cooper-Harper scale to account for the unique characteristics and operations of UAVs. The focus is on the UAV operator and UAV mission performance. This modified scale can be used for any UAV task. However, this modified scale is used to assess handling qualities, not flying qualities. From a flying qualities perspective, of all the unmanned air vehicles, the fixed-wing UAV most closely resembles an aircraft. The topic of aircraft flying qualities has been studied since before the Wright brothers' first flight in 1903. Conversely, the design and development cycle for UAV has not reached the same level of sophistication as that of manned aircraft. This includes the absence of a flying qualities standard too. The flying qualities of manned aircraft and UAVs have common aerodynamics and dynamic foundations, but differ significantly in how they are evaluated and applied, mainly due to the absence of an onboard pilot in UAVs. At this table, I summarized the differences and similarities between aircraft and UAVs. For example, in terms of human factors, the pilot's role is central to the aircraft, but minimal to the UAV, as the UAV is always autonomous. In terms of challenge, efforts should focus on balancing pilot workload versus stability and control. For UAVs, the focus should be on dealing with communication delays, autonomy validation scaling effects, and the absence of standardized test metrics. Considering these differences and similarities, the question becomes, is it possible to apply the flying quality criteria for aircraft to UAVs? To answer this question, we will start by reviewing the related literature. Traditional flying quality criteria for piloted aircraft, such as those in military standards, were developed around human pilot perception and control. Applying them directly to UAVs is problematic, since UAVs often operate autonomously or via remote control, where human workload and perception are less central. However, researchers have been actively exploring how these criteria can be adapted. For example, Holmberg et al. Note that current flying quality standards do not adequately capture the unique characteristics of UAVs, particularly in autonomous or remotely piloted context, and emphasize the need for update design standards specific to UAV applications. Similarly, Quoting argues that UAVs are at the same stage piloted aircraft were when flying qualities were first formalized, suggesting that a new generation of UAV-specific criteria must be developed. At present, there is no universally accepted UAV-specific standard for flying qualities of fixed-wing UAVs. The field is still fragmented, with different approaches depending on UAV size, mission, and level of autonomy. Holmberg et al. Showed that traditional manned aircraft specifications are not sufficient for UAVs, since they were built around pilot-in-the-loop performance. They called for entirely new criteria and design standards tailored to UAV operations. Studies on guidance and control for fixed-wing UAVs show that disturbances, sensor quality, and autonomy play a bigger role than in manned aircraft, meaning stability and control mergence need rethinking. Many newer works treat flying qualities in terms of formation flight, fault tolerance, and autonomy robustness. These works and studies emphasize cooperative control rather than pilot workload. This means that for fixed-wing UAVs, flying qualities are still research-driven and case-specific, not standardized across the industry. Developing a standard fixed-wing UAV flying qualities has been a recurring challenge in the literature, since there is no consensus yet. Researchers and regulators suggest combining lessons from manned aviation, autonomous control theory, and UAV-specific testing. Based on current research, here's what could be done. First, use aircraft metrics such as natural frequency or damping ratio as initial guidelines. Second, since there is no onboard pilot, metrics should emphasize autonomous stability, robustness to delays, and operator situational awarenesses. Also, mission-oriented flying qualities should be defined. Third, unlike manned aviation, UAVs lack a shared database of flight test results. Creating such a repository would allow comparison, calibration, and eventual codification of standard thresholds. Fourth, standardized simulation methods for pre-flight evaluation. Use hardware in the loop and low-cost flight testing for validation. Fifth, coordinate with civil regulators to align flying quality standards with UAV airworthiness certification frameworks. Also encourage mission-specific certification envelopes. Several methods have already been developed by tracking these suggestions. We can categorize them into two groups. The methods under first group treat existing pilot-centric standards as a foundation, then adapt them for UAVs. Three of them given here, Kotim, Capello, and Kim. These approaches use military-based stability, control, and response measures as a starting point, but adjust thresholds and interpretation since there is no onboard pilot. And they all mention the lack of a standardized UAV flight quality assessment method. Other researchers argue UAVs need entirely new criteria, given autonomy, remote piloting, and mission-driven constraint. Holmberg, Green, and Wang worked on developing new criteria. These approaches, under second group, emphasize autonomy, robustness to communication delays, and mission adaptability rather than pilot handling. Especially more recently, Wang et al. Proposed specific flying qualities requirements for autonomous combat UAVs, aiming to adapt traditional stability and control metrics for unmanned aircraft systems. Their simulation results indicate that existing flying qualities guidelines for manned aircraft are not fully applicable to autonomous unmanned combat aerial vehicle. The combination of bandwidth and phase at the bandwidth frequency was found to define the flying qualities requirements. Criterion boundaries for different levels are provided, and the physical reasons for the formation of the boundaries are analyzed. Their results can be applied to the assessment of flying qualities and the design of flight control laws for autonomous unmanned combat aerial vehicles. We have also begun evaluating the flying qualities of UAVs using our customized fixed-wing UAV. Although our research is not yet complete, we are working on a novel assessment method, and we reached some conclusions. Direct application of aircraft metrics is not fully valid for UAVs. Existing criteria can provide a baseline, but must be adapted. Research is moving toward UAV-specific flying quality standards, but the field is still developing. More studies need to be conducted to assess the flying quality of UAVs, which affect the sustainability and energy efficiency of flight. Thank you so much for listening. All questions are welcome. You can contact me by email.